Today we have a seminar by E.Tarjan from Princeton University and Intertrust Technologies. E.Tarjan is known for his foundational contributions to data structures and algorithms, which include many concepts that are now part of undergraduate textbooks, from depth first search to different types of search trees. And for these contributions, he received the Turing Award in 1986. And he's currently visiting Latvia for a few days in his capacity of chief scientist of Intertrust Technologies, which among other things owns a Latvian company called Whitecryption.
Thank you. No, I don't own it. It's not true.
Thank you. Well, it's a pleasure to be here today. Beautiful sunny day. We should be outside instead of indoors. Today I want to talk about a very simple kind of binary search tree. This is kind of a synthesis of known ideas. And this is joint work with my grad student, Caleb Levy. So let me start with some philosophical remarks. Computer science, as we know it, has been a field for maybe 60 years. It's existed for a little bit longer than the time I've been doing research. And during this period, computer scientists have developed lots of beautiful and theoretically efficient algorithms, but it's still a young field. I mean, mathematics, physics, chemistry are all much older. What this means is that we've also often settled for the first good enough solution, but it may not be the best because the design space is very rich. We're dealing with computers that run very fast, and as computers get faster and computer memories get bigger, the design space for algorithms gets even richer. I would say one problem of theoreticians is that they tend to develop algorithms with the goal of getting good complexity results, which does not necessarily produce simple algorithms. So my goal in recent years has been to try to identify the simplest possible methods for which one can still prove efficiency bounds. Paul Erdős, who was a famous mathematician, had this concept of proofs from the book. That would be the book up there. Proofs that were best possible in some sense. So our goal is to come up with algorithms of the same sort. Algorithms as simple as possible with provable resource bounds for important input classes and that are efficient in practice. One point here is that all these beautiful results that theoreticians have come up with, many of the algorithms are so complicated that no one is ever going to implement them. Much simpler algorithms work well in practice, and we would like to actually produce ideas that are useful in practice as well as theoretically beautiful. This quote is attributed to Einstein or some variant of it. Make everything as simple as possible, but not simpler. Sometimes simplicity is not only nice to have, but it's critical, especially if one is in a situation where you're trying to devise an algorithm for a multiprocessor system, a concurrent algorithm. It's hard enough to prove single processor algorithms correct, let alone analyzing their efficiency, but it's much harder to prove concurrent algorithms correct, so simplicity really pays off in this domain. So this data structure, as I said, it's not really novel. It's a combination of known ideas, but it's very simple. It's a form of binary search tree that uses randomization. I'll call it a zip tree. Zip because, as we'll see, this idea of unzipping and zipping comes into play in the implementation, and zip also means fast. So the goal here is speed and simplicity. So let's go back to our undergraduate data structures class and look at one of the most fundamental problems, which is to store a dictionary, collection of items, each with some associated information. We want to look up an item and return its information, and we want the dictionary to be dynamic. We want to do insertions of new items and deletions of old items, and possibly some more complicated operations. So if this is all we need to do, a hash table is the right solution. Constant time, access, insertion, and deletion, but a hash table scrambles the data. So if we want to preserve order, we need to do something a little bit different than a hash table. We need a data structure that models something like binary search. So binary search, the set of items is totally ordered, and we can search for an item using binary search. We start in the middle. We ask if our item is bigger or smaller than a given item. If it's smaller, we search in the small half of the set. If it's bigger, we search in the big half of the set, and we recurve. So instead of taking linear time to scan all the items, we take logarithmic time. So we get exponential speed up using binary search instead of linear search. Now we want to instantiate this idea in a data structure. Here's a binary search tree, which is a concrete representation of binary search. It's just a binary tree. Each node has two children, a left child and a right child. One can be missing or both can be missing. There's one item per node in the search tree, and these are arranged in symmetric order or in order, which means that for any given item, everything in the left subtree is smaller and everything in the right subtree is bigger. That means we can do binary search. If we want to search for G, for example, we start at F. G is bigger. We go to M. It's smaller. We fall off. We know G is not in the tree. If we want to search for P, we will walk down this branch of the tree. So these are the definitions. I will denote the left child of a node by x dot left, the parent by x dot p. A node is binary if it actually has two children, unary if it only has one child, or a leaf if it has no children. And I'll denote by n the number of items in the tree, the number of non-null nodes. A few more parameters. The depth is the maximum path length. Well, it's the length of the path from the root to the given node, and the depth of the tree is the maximum path length. We start at 0 and count down from the root. The height counts up from a node and up from the bottom. So the height of a missing node is -1. The height of an arbitrary node is 1 plus the maximum heights of its children. The size is the number of nodes in a given subtree. Now, to represent a tree in a computer, we need at a minimum pointers to the left and right children, or ways to get from a node to its left and right children. Sometimes we need additional pointers, such as a pointer to the parent. There are various kinds of threaded structures and so on, but for our purposes, all we're going to need is left and right child pointers. Now, we want the tree to be balanced. I'll get to what this means in a minute, but we may need to store additional information in the tree in addition to the pointers to the children, the values associated with the item in the node, and some kind of information associated with the structure of the tree. And in particular, I'm going to introduce a notion of a rank, which we're going to use to help balance the tree. All right, so a binary search tree is just a binary search tree, as I said, with one item per node arranged in symmetric order. The time to do a search is proportional to the maximum path length, the depth or the height. And our goal then is to minimize the height or the depth, to minimize the search time. And secondarily, we would like insertion and deletion. We want the data structure to be dynamic, so we want insertion and deletion to be fast. The time to search for the insertion position should be fast. It'll be proportional to the depth. And restructuring the tree should also be fast. And you can think of the restructuring part as separate. Searching just involves reading the tree structure. Doing insertions and deletions involves adding or deleting nodes and possibly rearranging parts of the tree. And let's think about this in a concurrent context where we have multiple searches going on at the same time. It's easy to allow multiple searches as long as you can read items concurrently. But if you want to start doing concurrent updates, then things get more complicated because you have to make sure that writes are not taking place at the same place. And in particular, we don't want the root to be a hotspot for insertions and deletions because everything proceeds from the root, at least in the simplest kind of binary search tree. All right, so I think we saw this example before. The best case of a binary search tree is where the nodes are packed as close to the root as possible. If the number of nodes is a power of 2 minus 1, we can exactly pack the nodes into levels so that all the leaves are at the same level at the bottom of the tree. In general, we can't do that, but we can pack the nodes so that all the leaves are in the bottom level and next to the bottom level. And then the maximum path length is binary log of the number of nodes, essentially. That's the ideal. We can achieve this in the static situation where we have the data ahead of time. But if we want to do insertions or deletions and maintain so rigid a structure, we have to do a lot of rebuilding of the tree, a lot of restructuring. Now we want a data structure. We're going to compromise on the maximum path length in order to make insertion and deletion more efficient, proportional at least to log n rather than linear, where we would have to rebuild the entire tree. The standard way to do, ignoring the balancing, the rebalancing question, the standard way to do an insertion is so-called leaf insertion. We start at the top, we search for the item, we fall off the tree at some position, and we insert a new node at the position where we fall off the bottom of the tree. So in this tree, if we want to insert R, we start at F, we follow the search path, which falls off the right child of P here, we would put R in here as the new node. That's all very well, except that if we start with an empty tree and we use this naive form of insertion, and we take a naturally occurring situation, just insert items in sequential order, we're going to get a very unbalanced tree. If we start out with an empty tree and we insert A, B, C, D, E, F, G, and so on in alphabetical order, we get this tree, which is no better than a path. The worst case search time is linear in the number of nodes. The average search time is linear in the number of nodes. This is terrible. So not only is the worst case bad, but this is a case that would naturally arise or could naturally arise. So we need to do something different if we want to maintain logarithmic search time. The first kind of balanced tree ever invented was the AVL tree. This is named after two Russians, Adelson-Velsky and Landis. They published a 4-page paper in 1961, which is before most of you were born, I guess, in which they described this notion and how to do insertions. This is a so-called height balance tree in which for every node, we look at the height of the left subtree, the height of the right subtree, and we make sure those are either equal or within 1 of each other. We don't need to store the entire heights at every node. It suffices to store a 3-valued state, which indicates whether the two heights are the same, or the left tree is deeper, or the right tree is deeper. And we can do rebalancing. I'll come to how rebalancing works in a minute. Since the invention of AVL trees, there have been many more such balanced tree structures, all of which involve some kind of local balance information and some kind of updating scheme based upon rotations that proceeds along the axis path. So red-black trees, how many people know about red-black trees? What did you get taught as undergraduates? Red-black trees, AVL trees, something else. B trees. B trees are like balanced search trees, only they're not necessarily binary. So red-black trees various kinds of AVL trees. There's a long list here, and they all work more or less the same way. The idea is that we're going to maintain some kind of explicit balance information that guarantees logarithmic maximum path length, and it is easy to update after we do an insertion or deletion. Speaking of deletion, the AVL tree paper, the original paper, as I said, is only 4 pages. The authors didn't talk about deletion. It fell to a United States aerospace engineer who wrote a technical report on how to do deletion in AVL trees. It runs tens of pages. Now, it's not that complicated, but one problem with balanced trees is deletion seems to be always more complicated than insertion, and people have gotten the deletion algorithms wrong. This gets back to this question of making things as simple as possible, but not oversimplifying. In any case, the classic solution to this efficiency problem was to have an explicit balance condition. But there are other alternatives. One is to have the tree somehow automatically adjust every time you do an operation. Danny Slater and I came up with this idea in the mid-'80s and invented a data structure called splay trees, where there's no explicit balance condition. But every time you do any operation on the tree, insertion, deletion, or even an access, you restructure the tree to improve it somehow. And we were able to prove nice properties of this data structure. But I'm not going to talk about splay trees other than to show a picture in a minute. And a third possibility, splay trees are deterministic. All these balance trees are deterministic. A third possibility is to use randomization. And that's what zip trees are going to do. All right, so here's an AVL tree. The +1 means that the maximum path length on the right side is 1 larger than the maximum path length on the left side. So this node is right deep. The maximum path length here is 1 longer than here. This is left deep, so the maximum path length going down here is 1 more than here. These nodes with zeros, the maximum path length down both sides is the same. Here's an AVL tree. Here, the balance condition, we only need a single bit of information in each node to store the balance information. The nodes are colored red or black. The properties that give balance are, for every path from the top to the bottom, the number of black nodes is the same. And we'll make the missing nodes here all black. So the black length down all paths is 3 in this case. The red nodes are introduced to give flexibility. The requirement is that a red node has a black parent. So you cannot have 2 red nodes in a row. All of the balanced tree data structures, along with splay trees, on insertion to deletion, we have to restructure the tree locally, and we do that by doing rotations, or more complicated operations that consist of several rotations. Like a double rotation is a pair of rotations done in a certain configuration. But a rotation is very simple. It involves a local restructuring that can be done in constant time, moves certain nodes in the tree up, pushes other nodes down, preserves the symmetric order so it preserves the searchability property. So in particular, if we have a left child of a node Y here, we want to do a rotation at this node X. This changes the left branch into a right branch. X moves up to the parent position, Y moves down to the right child. The 3 subtrees here get attached in the same left to right order. This preserves the symmetric order. And this node Y may have a parent. So if you count the number of pointer changes in this transformation, this node's child pointer has to be changed. This is either the left pointer or the right pointer. And this pointer gets changed for Y because it changes from X to whatever the node is here. And this pointer gets changed. So we got 3 pointers that get changed. Okay. Now here's a artist's conception of a splay tree, self-adjusting. In a splay tree, every time you do an axis, you do a sequence of rotations that move the accessed item all the way up to the root. And this is done in a very special way so that individual operations can be expensive, but if you do a long series of operations, it turns out that the total time added up over the operations is at most the number of operations times log of the number of nodes. And furthermore, this data structure has stronger properties. If there's some kind of bias in the access sequence or locality of reference or something like that, the structure takes advantage of those properties. But lots of rotations happening all the time, and the root is definitely a hotspot. So this is not a good data structure if you're doing concurrent operations, even though it has lovely theoretical properties. So let's turn to this notion of randomization here. I want you now to forget what you know about binary search trees, other than our goal is to make something that's as balanced as possible. And let's take some of those ideas and try to develop something from scratch. So the idea is we want to make sure that we have something that resembles the structure of a perfectly balanced tree. Now, what do we know about a perfectly balanced tree? Half the nodes are at the bottom level. Let's start counting from the bottom. Let's call that level 0. Half the nodes are at level 0, a quarter of the nodes are at level 1, an eighth of the nodes are at level 2, and so on. Let's try to approximate that using randomization. How are we going to do that? When we insert a node, we're going to give it a height, counting up from 0, or some approximation to the height. I'm going to call this a rank. We're going to give it rank 0 with probability a half, rank 1 with probability a quarter, and so on. Choose these values randomly. So this is a geometric distribution. And then have an insertion process that puts the node at the proper height. Now, we cannot do this exactly, but we can do this approximately, and that's in fact good enough. All right. So every time we want to insert a node, we'll think of flipping a fair coin, count the number of heads before the first tail. That's one way to do it. That gives us a rank. That tells us approximately where we want to put the node in the level structure. And we'll arrange the nodes so that they're in symmetric order and they're in heap order with respect to the ranks, which means that the rank of a parent is always at least as big as the rank of the children. Now, there are going to be ties in ranks, so we have to break the ties. And I'll break the ties in favor of the smaller value by key. So these trees are going to be right heavy in some sense. This is an arbitrary decision, but it has consequences that we'll see in a moment. All right, so a zip tree then is a binary search tree where every node has a rank chosen randomly when it is inserted, and the nodes are symmetrically ordered by key, heap ordered by ranks, with ties broken in favor of smaller key. This is the static definition. If we're given a set of items with a set of ranks, there is in fact a unique tree that satisfies both the symmetric order and the heap order. Here's an example. So the 0 rank nodes are at the bottom, the 1 rank nodes are at the next level up. Here we've got a tie, 2 3 rank nodes, and the tie is broken in favor of the smaller rank. And here's another tie. Rank H has rank 1, M has rank 1. H is higher up because it has smaller key. Okay. Now, one definition of, or one meaning of zip is to move very fast, but there's another meaning of zip, which is what a zipper does. It unzips and zips. And that brings us to how we're going to do insertion and deletion in this data structure. We are not going to use rotations, or at least we are not going to think about using rotations. We want something that is conceptually simpler and more efficient in that it changes fewer pointers. So we have to be able to insert a node at an appropriate height in the tree. The idea is going to be, we walk down to the appropriate, we generate a rank for a new item. We walk down the path until we get to the right level, looking at the ranks and following the search path for the item. And then we want to insert the new item. This is going to be if the item has rank 0, it's going to go all the way to the bottom, and depending upon the tie breaking, it may just go in the bottom. And that's a likely case because remember, half the items are going to have rank 0. So most of the action, it happens at the bottom of the tree, and we'll get back to this point later. But let's think about this in general. You have to be able to insert an item at a given height in the tree. It turns out back in 1980, Stevenson wrote a paper in which he described an insertion process that always inserts an item at the root instead of at a leaf. So the new item is always at the top of the tree. How do you do that? Well, you want to insert the new item at the root. You follow the search path, and the search path naturally decomposes into the values smaller than the new item and the values that are bigger than the new item, and you basically take the path apart, and that creates 2 paths, and the subtrees go along for the ride, and that's the unzipping process. Here's a picture. If we want to insert n into this tree at the root, we follow the search path, and as we do, we test against n. So f is going to be smaller, it's going to be on the left path. P is larger, it's going to be on the right path. H is smaller, m is smaller. So we're going to end up with this search path split into f, h, and m on the left side and p on the right side. And the various subtrees go along for the ride, and we end up with something that looks like this. Now notice we can do this in a purely top-down process, which is another nice feature of this data structure. Standard binary search tree structures like AVL trees, the rebalancing process happens after the insertion or deletion. You do rotations and rebalancing, recompute the balancing information going back up the tree. There are some balanced tree structures where you can preemptively rebalance walking down the path. But again, there are complicated cases. You have to do things based upon what the balance information is and what the local structure is. Here, I hope you'll agree with me, this is not complicated. You just do an unmerging of the search path. And deletion is exactly the opposite, but we haven't quite got there yet because this is only root insertion. But now we have the 2 pieces. We got leaf insertion and root insertion, and if you want to insert a new item in an arbitrary position, we just follow the search path down to the right rank level, and then we unzip the remainder of the path, and then we're done. So I wrote how this works, but a picture may be a better example. So here's a zip tree. I want to insert item J. I generate a rank for it, which turns out to be 2. I follow the search path, which is going to take me from F to P. These are higher in rank, so I got to keep going. Down to H, and now H has rank 1, but I'm inserting a rank 2 item, so the J is going to replace H. And the search path from H down is going to get split into 2 paths. In this case, it's a pretty small example, so the remainder of the search path is H and M. H is smaller, so H goes on the left new path, and M goes on the bigger new path. So we got the top half of the search path. We found the insertion position. J is going to replace H. Now we have to unzip the rest of the search path and glue things together appropriately. Now, another nice thing about this data structure is that deletion is exactly the opposite of insertion. The tree is uniquely determined by the keys or the node values and the ranks of the items. If we want to delete something, we search for it or we find it somehow in the tree. We zip together the two paths that would have been created had we just inserted that node. That is, we take a left step from the node and we go down the right path to the predecessor. We take a right step from the node, we go down the left path to the successor. We zip those two trees together. We merge the trees in rank order, breaking ties appropriate. Exactly the inverse of insertion, and again, this is a purely top-down process. So if we want to delete item P here, we take a left step and we're going to go down this path to M, which is the predecessor of P, and a right step and go down the left branch to Q. We got the JM path and the XRQ path. We're going to merge these into a single path, again in rank order with smaller items favored if we have a rank tie. So we delete P, we follow the two paths to the predecessor and to the successor, concurrently zipping these two paths together, and we get the updated tree. Now, again, in this, let's back up here. We deleted node P, but in the resulting tree, there's no evidence that P was ever in here in the first place. As I said before, the structure is uniquely determined by the ranks and the keys. So this is first of all, the data structure is unique, depending upon just the values, the tree structure. And it's history independent, which may have some useful advantages in situations where you want to truly erase history. In standard kinds of binary search trees, when you insert an item and you delete it, there's some kind of shadow left behind because the insertion-deletion process changed the tree structure, and it's not necessarily unique. It may be hard to interpret what happened, but here you're guaranteed there's no evidence that deleted items were ever in the tree in the first place. Now, what can we say about this data structure? First, the static properties. The expected rank of a node is constant, and the expected rank of the root, this is the maximum of a n geometrically distributed variables. It's binary log n plus a constant. The root rank is constant log n with high probability. The expected node depth turns out to be 1.5 binary log n plus a constant. And the tree depth is constant log n with high probability. So with high probability, the tree is balanced. You've got logarithmic search time, logarithmic insertion and deletion time, because the insertion and deletion processes proceed only along a single path. Furthermore, most of the action happens at the bottom of the tree. So the expected, let me back up for a moment. If you compare this 1.5 here, so a perfect tree, this constant would be 1. With AVL trees, the worst case height is about 1.44 log n. So you're giving up, have I got that right? No, it's worse than that. I think it's 1.58. So this is an expected value. AVL trees, you get a worst case value, which is slightly worse than this. I don't know how you compare the expected value to the worst case value, but this is a pretty small constant. Red-black trees are worse. You get a 2 here in the worst case. Insertion and deletion, most of the action is at the bottom of the tree. So the expected restructuring time, that is the expected zipping, unzipping time, is proportional to the rank. Essentially, the probability of a tie is 50%, right? So, and there's this right heavy feature. So This 1.5 comes from the fact that going down the right side, you've got the chance of half of having a tie. Going down the left side, you're always going to a strictly smaller rank. So that kind of justifies this. You need to do a careful analysis to prove that you actually get this bound, but it's not too hard to do. The expected insertion deletion time, the restructuring time, once you find a place to do the operation, is constant. And the probability of doing restructuring that takes k steps is exponentially small in k, because the probability of the rank being a given value is exponentially small in the value. And every time you take a step up the tree, every 2 steps you take up the tree, you got high probability that the rank goes up by at least 1. So you can do your insertions and deletions purely top-down using this very simple unzipping and zipping process. This data structure has a lot of potential for concurrent implementation, and actually we've been looking at concurrent implementations for it. But it is now perhaps time to compare to other data structures that you may have seen before. There are previous randomized binary search trees, notably the TREEP, which was described by Aragon and Seidel. They have the same idea of having a priority, something like the rank, but they select their priorities uniformly from some set of possibilities that's sufficiently high to avoid ties, like 1 through n cubed or something like that. This means that the number of bits you need to represent their priorities is roughly logarithmic, whereas with the ranks, as we've defined them, the number of bits you need with high probability is only log n, constant log n, or actually log n plus an additive constant. So what we've shown here is that you need a lot less information in the nodes to do the balancing. The other difference between zip trees and the TREEPs is that, at least the way Aragon and Seidel presented them, they did insertions and deletions using rotations. So the idea would be, if you want to insert a new item, you follow the search path, stick it in at the bottom, and then you rotate it back up the path until you get the heap order correct. So it's a top-down followed by a bottom-up process. That way of doing things avoids the complicated cases of standard balance trees, but you're still doing rotations, and the rotation process is bottom-up, which is not as nice if you want to do concurrent operations, where having all the information flow, all the updating flow, go from top to bottom is very nice. To do a deletion, you do the inverse. You rotate the item to the bottom of the tree and delete it. This is isomorphic to the this is the unzipping property when you do an insertion and you do the rotations bottom up. The end result is exactly the same, but it's done step by step, and you end up doing extra pointer updates that you really don't need to do. So if you do it by unzipping, you actually save some constant factor in the implementation, and you can do it strictly top-down, and the same for deletion. Now, maybe more interesting is the fact that a zip tree is a binary tree representation of another data structure that supports logarithmic search, the randomized data structure of Pew, called a skip list. Here's a tiny tree. So this is just like a zip tree, except that the priorities here are chosen from a bigger set of possibilities just to avoid ties. But you don't really need to avoid ties as long as there aren't too many ties. Now here's more interesting. A skip list is a very nice idea, but the implementation gets a little bit complicated. So the idea is, we have a list of items. We're going to construct a sequential list of them. We want to be able to search them fast rather than just sequential search. So with a certain probability, let's say probability 1/2 to make things simple, we'll choose each individual item to be in a sublist at the next level up. So here are the items. Here's the bottom level list, which contains all of them. We flip a coin, it comes up heads for 3. We promote it to the next level. Tails for 4, heads for 7, tails, heads. The next level up, we just have 3, 7, 14, and 17. And then for the ones that survive to this level, we'll flip a coin again, and these are the only 2 that survive, and nobody survives above that. So this is a set of lists, each one a sublist of the previous one, a sublist chosen randomly, with, in this case, probability of half. To represent this thing, this is a dummy header node, and some people who describe this put in a dummy tail node. This is a figure I got from Ostrovsky. And you have at each level left to right pointers. So how do you search this thing? You start at the dummy node at the top level. Suppose we're searching for 13.5 here. So we follow this pointer. This is 7. We have to go farther. We go over here. This is 17. This is too big. So we're somewhere between 7 and 17. Drop a layer, drop a level. 14 is too big, drop a level. 12 is too small, 13 is too small, 14 is too big. We're at the bottom level, it goes in here. Conceptually very pretty, but if you want to actually implement this thing, you get variable sized nodes here, or else you have to put in a separate pointer structure to somehow represent these variable sized nodes. And then you got to make sure that the insertions and deletions work correctly. But conceptually, what is going on here, let's do the following translation. Let's take the height of these nodes to be a rank, and let's convert this to a binary search tree. We get exactly the zip tree representation. There's an isomorphism between zip trees and the corresponding skip lists with probability, with the p-value chosen to be a half. And actually, going back to the zip trees, instead of flipping a fair coin to choose the ranks, you could flip a biased coin to choose the ranks, and then you would get a data structure isomorphic to skip lists with a different choice of probability for the sample probability. And if you think about it a little bit, you can work out the mapping of the pointer structure back and forth. And the binary search tree version has the advantage that the nodes are simple. Every node has 2 pointers. You don't have different kinds of nodes. And the search is more efficient because there are redundant pointers in this structure, as it turns out, unless you take special, do certain kinds of optimizations to speed things up in this data structure. So this is kind of a reinvention or an optimization of an existing data structure, or 2 different data structures. So the original motivation here was to look at concurrent search trees and to come up with, first of all, what is the simplest possible sequential binary search tree that you could then represent in a concurrent or implement concurrently. The next step is to try to come up with a good concurrent implementation of zip trees and to prove good bounds. And the conjecture is that the hope is that somehow you can prove bounds on insertion and deletion time, where the time to do an update is proportional to log n, which is the search time, plus something which is logarithmic or polylogarithmic in the number of concurrent threads that are running. You're going to have the whole issue with concurrent data structures and concurrent algorithms is if things are embarrassingly parallel, you need no communication among processors. There's no interference. Everything is good. Everything scales wonderfully. But if you're in a non-trivial setting where processors have to communicate with each other or interfere with each other, then you have to worry about the interference. And to try to avoid linear or possibly worse blow-up in terms of the number of processors, this is a hard problem, as it turns out. So work in progress, we'll see where this goes. So to summarize, insertions and deletions are very simple, efficient. Most of the work is at the bottom, so constant expected time restructuring for insertions and deletions. Everything is purely top-down. Very short programs, no cases as in ABL trees or red-black trees. The data structure is history independent. There is no restructuring if you're just doing lookups, unlike splay trees where rotations are taking place constantly. As compared to skip lists, we're dealing with a standard binary tree representation, which is more efficient than this multiple layer of lists idea. Isomorphic to skip lists, but more efficient by some constant factor. And all the analysis that Aragon and Seidel did for trees applies to zip trees. So for example, they looked at ways to modify the priorities to support frequency biased access. So the idea is, suppose that we want to somehow exploit the fact that some items are accessed much more frequently than others. How can we do that? Well, you draw a new priority, sample a new priority for each access, and you redefine the priority of an item to be the maximum of the priorities. You can do the same thing with the ranks in zip trees. If you end up with a rank that's the same or smaller than the current rank, you don't have to do anything. If the rank increases, you need to do a rotation to move the item up. Very simple. It's extremely unlikely that things are going to move up and down. But what happens then is that an item ends up at a tree height which is proportional to 1 over the access probability, the empirical access probability, which is the total number of accesses so far. Let's see, the total number of accesses so far of the given item divided by the total number of accesses so far. So frequently accessed items are higher in the tree, less frequently accessed items are lower in the tree. The updates are very efficient, and this is best possible to within a constant factor by entropy arguments, assuming that all you know is that certain items are accessed more frequently than other items. So if you're in a model where every item is going to be accessed with a given frequency, given probability, but you don't know what that probability is, this data structure adjusts to become optimum in that setting. So I think I'll stop at this point. We put a paper on arXiv that we're in the process of submitting. That's the reference, and I'll be happy to answer questions if you have any. Thank you.
How much does it depend on the random number generator? What qualities of random numbers are required here?
That is an interesting question. That is, how many actual bits of randomness do you need for this process? We have not carefully explored that. That is, how much independence do you need in the random number generator? How much true randomness do you need? I think that's a good question. I don't think Aragon and Seidel looked at that, to my knowledge. I think that's a good question. In general, it's always good to have the best possible random number generator in these sorts of settings. Also, there's this issue with the ties, which are not terribly important. But there is a way to break ties by allowing fractional ranks, and then we get elimination of ties, and we can do it with just a small number of extra bits. So we can preserve the log-n number of bits per rank, which gives us an exponentially smaller number of bits than the naive idea of having uniform a uniform probability distribution over the ranks. Yes.
Is there some fundamental workaround around the concurrency problem? You specified that you try to minimize the effort to rebalance the tree, but
Yes.
is there some fundamental way to, like, for sure not have that problem? If you have multiple searches, as you mentioned in the beginning.
As long as you have reads only, it's
then there's no problem.
writes, it's still a challenging research problem, actually. So the model here is, if you want to get an efficient concurrent data structure and you use locks, it's kind of game over, because if one process locks a node and goes to sleep, and everybody else is locked out. So there are these wonderful ideas for lock-free, wait-free, non-blocking, there are different terms, techniques to avoid this problem. So that you want a very general model where you don't know the relative speeds of the various processes. You want to allow processes to fail without spoiling things for everybody else. That's the setting in which we're trying to do analysis. And then what you have to have, we're trying to do multiple insertions in the same place. If somebody starts to do an insertion and goes to sleep, you need a way to record that information so that some other process comes along and can do the necessary update, and then it can go back to doing its own update. There's a lot of work in the field for lots of data structures, including search trees, and it gets very complicated. Getting things correct is an issue, let alone getting things efficient. So as far as I can tell, this is still, interestingly, in the concurrent setting, some of these fundamental questions are not completely answered yet. So as far as I can tell, this is still an active area of research. Yes.
What are the best currently known solutions for concurrent data structures?
It depends upon what data structure you're talking about, I guess. There are concurrent implementations of skip lists and various kinds of balanced trees. Another thing that has been tried is the idea of separating the rebalancing from the lookup and insertion process. So you do rebalancing, say, using rotations, but you have some separate process that's updating the tree as you go along. The problem with that is there are these bad cases, like if you insert things in alphabetical order. I showed that in the beginning. You get a long path, and then it's going to take a long time before you get a balanced structure. So those solutions don't necessarily seem so robust to me. I haven't got a good answer. Well, so in this model where you want to allow processors to have arbitrarily different speeds and to be able to die and still have things robust, I know of very few results where there's an efficiency bound that's sublinear in the number of processors, which is what you want if you actually want things to scale. There's a nice result by Faith Ellen and a colleague of hers on a fetch and increment object. So the idea is you have a counter, and you have multiple processes, and all they want to do is update the counter and get the next value. You got P of them, so there would seem to be P-way contention. They have a way to have everybody get a value of the counter and have the counter get incremented, but they can prove a log P contention bound, basically. It's with a nice binary tree structure, very interesting. And I think the same idea, or I hope the same idea, or something like it, I think the randomization here will help in the binary tree setting. There's no such result for surge trees. The contention is at least linear, as far as anybody has been able to get so far. I've been working on concurrent data structures the last maybe 4 years, actually, and we looked at disjoint set union find, which you may or may not be familiar with. But in the sequential world, there's an inverse Ackermann function bound for a very simple tree-based data structure. And this data structure, interestingly enough, if you define the problem right, you can avoid the root being a hotspot. And together with Siddhartha Jayanti, who was an undergraduate at Princeton and is now a grad student at MIT, we were able to extend some of the sequential results to the concurrent domain. So we have concurrent algorithms for which we can actually prove some kind of logarithmic contention bound in this very general model, if we define the problem in the right way.
Well, and still the Z trees really tells certain nice properties, but assuming that you are interested only in implementation of search tree with maximal possible speed, let's say, and you look for average time, how well these Z trees will compare with others, and the related question really is the best possible search tree regarding implementation, or it's not answerable question?
Well, I think it's a reasonable question. We haven't done careful experiments. I'm sure it's in the ballpark, however. It's a subject for experimentation, definitely. I would also say that in the concurrent world, this property that most of the updates are at the bottom of the tree means in practice you can get away with some simple local locking scheme, and you will probably get something that's extremely efficient. But there's a lot of practical work to be done here. People certainly use trees in practice, and this is a simplification of trees. They also use zip trees in practice, and this is a simplification of of skip lists. So I think it deserves to be studied empirically, but we haven't done it yet. Yes.
Was the right heaviness of the tree actually a problem? You said the ties are broken by keys, right?
You could break, the reason we broke ties in the right heavy direction was to make the mapping, the isomorphism with skip lists as transparent as possible, or as simple as possible. You could break it in favor of left heavy trees, or you could break it arbitrarily. What does it cost you to allow ties? If you didn't have ties, you wouldn't have this tie breaking question. It costs you about 4%. The average case height bound for zip trees is the same as for random binary search trees, which is something like 1.44 binary log n versus 1.5 for this data structure. So it doesn't cost you very much, actually. And as I said, if you add some extra bits, if you define a fractional rank, you can get rid of the tie breaking. But I think you lose in simplicity more than you might gain in efficiency. I don't view 8% as significant. Any more questions?
About block deletions, can we mark some items for deletion? Because we don't have time for that at that point, so some sort of accumulated complexity and then delete all of them.
Probably. That's probably a good idea, definitely. Also in the concurrent setting, people have looked at this idea of doing block insertions, block deletions as a way of avoiding contention. We haven't looked at that, but I think that's a promising idea.
So
Yes.
I think you do mention in the paper that if the adversary knows the rank that you're generating, you can generate the worst case tree with a dash of half of a node.
Yes.
So if I understand correctly, you suggest you can use lazy deletions to solve that. So can you elaborate a bit more, like when would you actually perform the deletions itself?
Well, imagine the following case. An adversary is watching the ranks. Okay, so you start generating ranks and inserting nodes. Every time you generate a non-zero rank, the adversary says immediately delete that item. So everything gets rank 0, and you got half the items with rank 0, you're going to end up with the long path. That's the bad case. How would you fix this? You'd have to, I think the simplest thing to do is to start using fractional ranks, but it is still true that the adversary could foil things, but maybe not as badly. You might get square root of n path lengths or something like that. Is that a problem? It depends upon whether you believe in adversaries. In practice, people are, I think this is mostly a theoretical question. Your computer system, we hope, is not conspiring against you in this way. But people in the theory world go out of their way to try to deal with adversaries or prove that it can't be done. But in practice, I don't think this is an issue.
So similar question, the historical property that it retains no history.
Yes.
So in that, like I'm thinking security, right? So like,
Yes.
can you talk a little bit more about where that would be important, or it's an interesting observation, but it's not
Yes, and it is not mine. To get, in fact, you cannot do it. It seems, I don't know if there's actually a proof of this, but there may be a proof that if you have a deterministic data structure, you can't get this history-independent property and have efficient insertion and deletion algorithms. There's some kind of trade-off. So the randomization is critical to getting the property. Whether it's actually good for anything or not in practice, I have no idea, but it's a nice fact about this data structure. And there have been papers on this sort of thing. Yes.
Have there been any research that proves that or utilizes the fact that some nodes can be accessed more frequently than others? Like sometimes the searches for specific nodes happen so rarely that it maybe pays to put it as a leaf, and some are so frequent that it pays to sort of move it more up closer to the root so that the path would be shorter.
So two answers to that question. With this data structure, and actually originally with TREEPS, if you generate a new priority or a new rank every time you access the item, and you always maintain the maximum priority, then the frequently accessed items tend to move up in the tree structure. And the path length, the expected path length down to an item is proportional to the log of 1 over the access probability, which is exactly what you want.
Mm-hmm.
So if you're in a situation where you have the simplistic notion that the access frequencies are the same over time, the access probabilities are the same over time, this kind of data structure you can make work in that context. Now, splay trees have a much more powerful property that we can't actually, we can prove various versions. For different kinds of locality of access, you can prove that splay trees do really well. For example, if there is a small set of items that are being accessed and nothing else for a while, that set of items will move to the top of the tree and will get accessed cheaply. If the working set changes, that set gets promoted. You can quantify a measure of efficiency in that kind of context, and you can prove that splay trees do best possible in that scenario. We have this conjecture from our original paper that says that in the binary search tree model, so here's the setting. You have a fixed set of items. Let's forget about insertions and deletions. You've got an n-node search tree. Let's say you know what it is originally. You're told to do a sequence of accesses. Your cost is the length of the access. To do an access, you have to walk down the path, so it's the depth of the access node. You can also at any point do a rotation in constant time at constant cost. So your total cost to do the access sequence is proportional to the sum of the depths of the accessed items when you do the access, plus the total number of rotations. So now I have an initial tree, I have an access sequence, if I know the access sequence ahead of time, there's some optimum algorithm, offline algorithm, I don't know what it is. The conjecture is that the splay tree data structure, this very simple online restructuring process, comes within a constant factor of the optimum offline algorithm on any access sequence whatsoever. This conjecture has been open since 1983, I guess. So this data structure seems to capture any possible locality of reference that can be captured in the binary search tree model without making the data structure much more complicated. No proof, but no counterexample either. And there's reason to believe that it's actually true now, I think, but still no proof.
You said that the rank will increase if you do more lookups. What happens in that case? Like, you're unlucky and you have 3 items and you get rank 1 for all 3 of them. How you order them?
Then you're going to get a long,
But it's all rank 1. There's no leaf then.
Oh, well, the biggest one will be a leaf, right, because the only property is that they're heap ordered with respect to the ranks and symmetric ordered with respect to the keys, right? So if you have no zeros, there aren't going to be any zeros in the bottom of the tree, right? The smallest one will be at the top, the next smallest one will be the right child, and the next smallest one will be the right child of the right child. So you end up with a path with 3 nodes, all of rank 1.
So the average rank doesn't matter. It can inflate over time. That wouldn't matter. But then the number of bits in it for the rank increase over time as you get more.
Yes, that's true. So if you were actually going to use this idea in practice, you would want some way to deflate the ranks or something like that. And this, I think there are interesting questions in there, and I don't have the answers for them. I mean, in fact, in any realistic scenario, you probably don't have global fixed access probabilities. Things change over time, and you would somehow like to give more weight to recent accesses than to less recent accesses. As I said, the splay tree data structure, in fact, does that. This kind of global data structure doesn't, so you'd have to use some more dynamic way to update the ranks. You'd want to decrease the ranks of the items that haven't been accessed recently somehow. I think it's an interesting question, how to do that.
You mentioned that one way to reduce dice is by using fractional ranks.
Yes.
How does this fundamentally differ from just increasing the number of ranks by using biased point rendering them?
I think it is more efficient. But I haven't looked at the numbers carefully. The point somehow is that you are exploiting the fact that things are getting spread out by the search tree process. I don't know exactly what to say about this. So maybe I don't have a good answer for you, but I think it's more efficient to add fractional bits at the end because you only have to break ties down at the bottom, basically. You add bits at the high level and it doesn't really matter very much. That's not a very good answer, I'm sorry. Any more questions? Thank you very much.
Thank you.